The towers at Mono Lake have been building for 50,000 years. They rise from the water in pale gray columns, stacked and curved. Some of them stand 30 feet tall above the eastern shore. They form where calcium spring water rising through the lakebed meets the carbonate-heavy lake above. When that specific chemistry breaks down, the towers stop building and start to erode. By the late 1970s, the towers at Mono Lake were eroding. The water had dropped far enough that most formation zones sat exposed in open air. The lake was getting saltier each year as its total volume shrank. Biologists who studied the site used the phrase terminal decline in their field reports. They meant it the way a physician means it, not as a figure of speech. Today, the towers are building again in the submerged zones where the chemistry still holds. The lake surface has risen 25 vertical feet from its lowest recorded point. The bird colonies are back in numbers larger than the pre-crisis surveys showed. The sediment community at the bottom, which had shifted heavily towards salt-tolerant extremophile organisms, is restructuring. Scientists are still publishing papers trying to account for exactly how fast any of this happened. The man who knew this lake more closely than anyone else died in January 1989. He never lived to see a single foot of what came back. David Gaines drove to Mono Lake from Berkeley in early September of 1976. He was a graduate student in ecology, 29 years old, assigned to study shorebirds. His dissertation committee had asked for waterbird population data from a set of Great Basin sites. Mono Lake appeared on his list as one entry among several, without particular distinction. He set up a canvas camp on the eastern shore and started his morning bird counts. The lake sat in its basin at 6,300 feet above sea level. Volcanic ridges flanked the water to the east and to the north. The Sierra Nevada rose to the west and threw its shadow across the surface each afternoon. There were no trees near the shoreline, just white crystalline flats and gray tufa columns. The watermarks on the volcanic cliffs above him were not where the water surface was. Each horizontal stain on the rock marked a previous shoreline from an earlier year. They rose well above the current level, stacked in lines he could count and read like a chart. He calculated the vertical distance from the highest visible mark down to the present surface. The number was roughly 30 feet of lost elevation across 3 decades. His published notes from that visit record the observation without drama. He wrote that the lake appeared to be losing volume at a measurable and ongoing rate. He drove back to Berkeley at the end of 2 weeks and told his advisor what he had found. His advisor said the eastern Sierra water situation was well known and extremely complicated. He suggested Gaines finish the bird survey and advance his dissertation on the original schedule. Gaines agreed and said he would come back the following spring to close out the count. He returned every spring for the next 13 years. To understand why Mono Lake could die at all, you have to understand what it was. Mono Lake is a closed basin with no outlet to any river or ocean. Water enters from the surrounding mountains through streams, springs, and rainfall. The only way water leaves is through evaporation from the lake's exposed surface. Every mineral arriving with the snowmelt and rain stays in the lake permanently. Over 700,000 years of accumulation, the chemistry became extreme. The pH sits between 9 and 10, well beyond what most organisms can survive. The salt load includes carbonate, chloride, and sulfate compounds in high concentrations. 2 species had evolved to thrive in precisely these conditions, and almost nowhere else on Earth. The first was a brine shrimp called Artemia monica, a subspecies found only in this lake. These shrimp grazed on photosynthetic algae and microbes distributed through the water column. In peak summer months, they could be dense enough to turn the water orange from the air. Every migratory bird stopping at Mono Lake was stopping almost entirely to eat them. The second species was an alkali fly called Ephedroians, found here in enormous numbers. These flies bred in the mineral crust along the tufa shoreline and tracked the water's edge with precision. Their larvae lived in the shallow margins where spring water pushed up through the lakebed. Remove the streams and you pull the thread the whole system hangs from. The Los Angeles Department of Water and Power pulled that thread in 1941. The four main feeder streams, Lee Vining Creek, Rush Creek, Parker Creek, and Walker Creek, all poured into the lake from the Sierra. The DWP turned them into the Los Angeles Aqueduct and sent the water 400 miles south. No environmental review governed this decision because no such process existed in California in 1941. The lake had dropped in previous drought cycles, but the diversion pushed the loss far beyond any natural variation. Between 1941 and 1982, the surface fell 45 vertical feet from its pre-diversion level. The salinity over that same period roughly doubled from an already high baseline. The total water volume in the lake had dropped by more than half. The city knew the lake was shrinking. The DWP tracked the level as an operational variable. Internal memos from the 1960s referenced the declining lake without expressing concern about its biology. They were operational documents that tracked the aqueduct system, not the lake biology. The lake was a figure in their calculations, not a living system. State agencies received reports on the diversion throughout the 1950s and 60s and took no formal action. The legal question of whether a municipal water right could override a terminal lake's biological functioning had no answer yet. It would not have one in California law until 1983. In 1978, the National Audubon Society began building toward that answer in the courts. The same year, Gaines founded the Mono Lake Committee in a rented space in the town of Lee Vining. The legal case and the scientific monitoring program ran on parallel tracks, and both needed the other to succeed. If you have been watching this channel and haven't subscribed yet, now is a good time to fix that. We post stories like this one every week, and the algorithm will not reliably surface them to you without a subscription. Negat Island sits in the southern part of Mono Lake, roughly a mile from the nearest shoreline. California gulls had nested on the island for as long as any historical record of the place goes. The volcanic rock provided predator-free ground and water far too saline for mammalian swimmers to cross. The island worked as a refuge precisely because the surrounding water made it one. In the spring of 1979, the falling water level opened a land connection from shore to the island. A narrow strip of exposed lakebed appeared between Negat and the south shore, roughly 30 yards across at its narrowest. It was pale mineral crust and damp gravel, not dramatic in appearance. It was also dry enough to walk on. Coyotes found the crossing within weeks of the strip becoming passable. The gull colony on Negat at that point held an estimated 50,000 birds. The coyotes reached the nesting area during the active breeding season. The birds did not thin gradually over several years of pressure. They abandoned the colony site almost entirely within one breeding cycle. Secondary nesting locations were documented across Nevada, Utah, and Northern California in the years that followed. Gaines photographed the land bridge from the south shore and sent the images to every newspaper contact he had. He described the colony collapse in written testimony before state water agencies and at public hearings in Sacramento. He calculated, using the DWP's own published lake-level data, what continued diversion would cost every passing year. He presented those numbers to officials, journalists, school gymnasium audiences, and university lecture halls. People who attended those presentations describe a specific quality in how he spoke. He did not perform alarm. He presented the data precisely and let the numbers carry the weight. He knew the lake's exact level in any given month, the shrimp counts by survey zone, the fly population by individual shoreline segment. He could recite all of it from memory. The calm made the data harder to argue with than outrage would have. The diversion continued on the schedule the DWP had always run. Gaines continued every monitoring count on the schedule he had always run. The 50,000 gulls that had been eating brine shrimp at Mono Lake every summer were scattered across 3 states. The shrimp those gulls were no longer eating went largely ungrazed through the summers they were absent. The food web operating at the lake was running under conditions it had not experienced in any part of its recorded history. The National Audubon Society's lawsuit against Los Angeles had been moving through the California courts since 1979. By 1983, it reached the California Supreme Court, which issued its ruling in September of that year. The court did not directly order the city to stop diverting water from the feeder streams. What it did was establish that the public trust doctrine applied to those streams and to the lake they sustained. Los Angeles contested the practical application of the ruling at every court level available to them. The process would take another decade before it produced any concrete water level requirement. Gaines understood the legal timeline would be long and kept working at the same pace. His monitoring program had grown from a solo count into a network of trained volunteers running multiple survey sites. The Mono Lake Committee was publishing annual reports with specific numbers, not general statements about the lake's deterioration. The data was on the record in a form that courts and agencies could actually use when the time came. On January 5, 1989, Gaines attended a meeting in Mammoth Lakes connected to the ongoing water case. He had a state agency hearing scheduled the following morning in Sacramento and needed to drive north overnight. The road through the Sierra Nevada in January ran across ice and compacted snow. His truck left the road on a curve above the town of Lee Vining. He was 41 years old, with 13 years of unbroken lake data behind him. He had monitored this lake for 13 consecutive years without a single gap in the field record. He had trained the volunteers who would carry the monitoring forward in his absence. He had helped construct the legal argument still working its way through the California court system. The committee he had founded in 1978 released a statement saying the work would continue. Both things he had built, the organization and the data set, proved more durable than the person who built them. The lake's recorded low point had come in 1982, 7 years before his death. After that, the level had stabilized in a narrow range, fluctuating with rainfall, but not recovering in any measurable way. He had documented the decline from its early measurable years through nearly its full extent. He did not see the water rise by a single recorded foot. The California State Water Resources Control Board issued Decision 1631 in September of 1994. The order established a target water level for Mono Lake at 6,392 feet elevation. Los Angeles was required to allow substantially greater stream inflow until the lake reached that level. Diversions were restricted above a minimum threshold until the target was confirmed. The negotiation over the specific elevation had been complex on both sides. Environmental groups wanted a higher target that would restore pre-diversion conditions more completely. Los Angeles wanted a lower target that preserved greater access to eastern Sierra water. The number that emerged was a compromise both sides could formally accept. Restoration crews began working on Rush Creek and Lee Vining Creek in early 1995. Rush Creek ran south from the Sierra through its original channel for the first time in several decades. Lee Vining Creek carried winter and spring snowmelt directly into the lake rather than into the aqueduct. Crews cleared debris from channels that had silted and collapsed from years without any water flowing through them. The lake surface was at 6,372 feet when the order took effect. Hydrologists built models predicting when the lake would reach 6,392. Their estimate was 25 to 35 years based on average precipitation and measured stream inflow rates. The models were peer-reviewed, published in journals, and presented to the agencies managing the recovery process. They were also, at several distinct points across several separate parameters, wrong. If you are watching this channel for the first time, we post stories exactly like this one every week. Subscribe and turn on notifications so you don't miss what comes next. The lake rose roughly 2 feet in the first 3 years after the order, which matched the model projections. Beginning around 1997, though, the biological data started running ahead of where the models placed it. Brine shrimp densities in certain zones reached pre-diversion survey benchmarks far ahead of any published timeline. Artemia monica reproduces fast under the right conditions, but the conditions in 1997 were far from ideal. The salinity was still well above the pre-diversion baseline. After those adjustments, the shrimp numbers were still ahead of the curve the models had described. One paper from that period described the pace as inconsistent with the predicted trajectory at current salinity levels. In scientific writing, that language is about as direct as the genre allows when something unexpected is happening. The alkali flies showed the same pattern in their own recovery data. Ephedra hyans is a shoreline specialist with habitat requirements closely tied to the position of the water's edge. As the lake level rises, the suitable shoreline shifts upward along the tufa, and the flies are supposed to track that shift. Studies of comparable saline lake systems predicted a lag of 2 to 3 years before fly populations re-established along a new shoreline. The lag observed at Mono Lake was closer to one full breeding season. When the feeder streams began running again in 1995, the land bridge to Negat was still open. The lake had not yet risen enough to submerge the strip of exposed lakebed that coyotes had crossed in '79. By the standard that had driven the birds away, the island was not yet protected. The gulls started returning to Mono Lake in 1996, 1 year after the streams reopened. They did not wait for the land bridge to disappear before establishing nesting sites at the lake. They settled on rocky outcrops near the water, while the bridge to Negat was still above the surface. Ornithologists who monitored the colony noted the return and the timing with visible puzzlement in their field notes. The birds came back to a lake that was still objectively worse by every measurable resource metric than when they had left it. By 2000, the breeding colony at Mono Lake had grown to 85,000 birds. That number exceeded the pre-land bridge colony estimate of 50,000 by a substantial margin. The birds came back larger in number to a lake still below its target, on an island still connected to shore. Papers published on the return proposed mechanisms involving competition pressure at secondary sites and individual bird site fidelity. Those mechanisms are plausible and compatible with each other and remain under active discussion. Below the shrimp and the flies and the birds sits the layer that drives all of them. The sediment at the bottom of Mono Lake holds microbial communities that have been there since the lake formed. These organisms photosynthesize, cycle nitrogen and sulfur, decompose organic material, and produce the base of the food chain above. In an extreme alkaline and saline lake, the microbial sediment layer is not background detail, it is the foundation the rest of the food chain is built on. When the lake salinity doubled between 1941 and 1982, the sediment community shifted. Organisms tolerant of extremely high salt and pH became the dominant members of the community. Organisms that had been common at lower salinity levels retreated to undetectable presence in sediment cores. Scientists sampling the lake bottom during the 1980s found species not cataloged in any prior Mono Lake study. Data from Mono Lake in the late 1990s showed structural changes in the sediment community within 2 to 3 years. The chemistry the models said the organisms needed in order to recover was not yet present. The salinity was still far above the pre-diversion level. The pH was still at the high end of its extreme range, but the community was restructuring on a timeline the models said those conditions could not yet support. Researchers proposed mechanisms including dormant cell reactivation from deeper sediment layers and broader tolerance ranges in the local strains. They noted that Mono Lake's specific chemistry may interact with biological recovery in ways that do not generalize from other saline sites. All three possibilities have been discussed in the published literature. None of the three has been confirmed by subsequent research. Papers continue to appear in the Journal of Paleolimnology and in quaternary science reviews addressing specific aspects of the sediment community. The full explanation for why the microbial restructuring moved as fast as it did remains an open question. The land bridge connecting Negat Island to the south shore finally submerged in the winter of 2016 to 2017. A sequence of wet storms raised the lake level above the bridge threshold over the course of several weeks. A monitoring team on the south shore documented the submergence over the final days before the strip disappeared. The narrow gravel crossing went below the surface at its lowest point first, then the rest followed. The submergence came later than the 1994 models had projected. Drought conditions through the 2000s and into the 2010s had slowed the lake's rise below average precipitation assumptions. This was the one part of the recovery that ran consistently behind the projections rather than ahead of them. Insufficient precipitation was the cause, not any failure in the biology of the lake. When the bridge went under, the gulls had already been nesting on Negat Island for years. They had returned to the island and rebuilt their colony before the water protection it required was actually in place. The ornithologists who documented the submergence noted the relevant event had preceded it by more than a decade. The birds had judged the island safe long before the water level confirmed it by the 79 standard. In 1987, 2 years before his death, Gaines wrote a letter to a colleague at UC Davis. The letter covered the legal case, the political obstacles, and his read of the lake's current condition. Near the end, he wrote something that had not appeared in any of his formal published papers. He wrote that he was not worried about the lake's ability to recover once the water was allowed to return. He wrote that the biology and chemistry of Mono Lake were more resilient than the pessimistic assessments assumed. He said the shrimp, the flies, and the tufa formations were adapted to this specific place across hundreds of thousands of years. He said that degree of adaptation was not going to dissolve under a few decades of human-caused stress. He expected the recovery, once it began, to move faster than the models being built at the time would predict. The letter was not peer-reviewed. It was not submitted to any journal or presented at any conference. It was a private document written by a man who had been counting shrimp at this specific lake every month for 11 straight years. The formal models built after him used data that he and his volunteers had collected across those 11 years. Those models did not capture the intuition that 11 years of direct field counting had produced in the person doing it. The recovery validated his intuition more fully than it validated the formal models at nearly every parameter where they diverged. The discrepancy was not inexplicable in every technical detail, but it was consistent across enough separate parameters to constitute a pattern. That pattern is acknowledged in the peer-reviewed literature, across multiple papers in multiple scientific specialties. What the literature has not yet produced is a unified account of why the recovery moved the way it did. The lake surface in 2025 sits at approximately 6,381 feet elevation. That is 11 feet below the pre-diversion level recorded before 1941. It is 25 feet above the recorded low from around 1982. The target elevation of 6,392 feet remains achievable in above-average precipitation years. Los Angeles still diverts a reduced volume of water from the Mono Basin under the 1994 terms. The DWP has invested in alternative sources and conservation programs to offset the Eastern Sierra reduction. The lake is monitored year-round by the Mono Lake Committee, using field methods that trace directly back to Gaines. Those methods have run continuously since 1976, nearly 50 years without a gap in the field record. The tufa towers exposed above the waterline are structures from the formation period before the diversion began. Below the current surface, at spring sites where the chemistry is still right, new towers are building. Visitors photographing the exposed columns from the shore cannot see the ones still forming beneath the water. The same process that made the visible towers is still producing new ones in the invisible zone below. The California gulls come back to Negat Island every spring, in numbers the pre-crisis surveys did not record. The brine shrimp bloom through summer in the southern and central portions of the lake. The alkali flies cover the shoreline tufa in densities consistent with long-term monitoring averages. These are data points from field records maintained without interruption since 1976. What has not been fully resolved is the question of speed. The lake came back faster than the models predicted, at multiple points, across multiple biological and chemical parameters. Papers continue to address specific aspects of this discrepancy, and the answers continue to require more data. The lake keeps generating results that the papers have not yet caught up to. The man who would have had the most grounded perspective on all of it died on an icy road 36 years ago. His field notebooks are archived at the University of California. His monitoring program still runs, staffed by people, trained by people he trained. His 1987 prediction about the resilience of this place has held up better than the formal models built from his data. The lake recovered in ways the science had not fully anticipated. That statement is in the peer-reviewed literature. The complete account of why it happened that way is not. If you want to keep watching stories like this one, the next video is on your screen now. We find these stories because you keep sharing the channel. Thank you for watching.